Hello, welcome back. We've been discussing this idea of pressure and density, and in this video, we're going to focus on some problem solving with them. And as I go throughout, I'm going to describe some certain steps that you might want to take and some things to watch out for. So let's take a look. In this first problem, we read that gold is sometimes sold by the troy ounce, and it gives us the mass of a troy ounce. And then it asks us what the volume of the troy ounce of gold is. Now, this is important because we are given three pieces of information. We're given the material, we're given the mass, and we're asked for the volume, right? Those are the three things at play here. And whenever we have these three quantities at play, we need to understand that the relationship between them is this density relationship, where density, represented by the Greek symbol rho, is related to mass, which we represent with M, and volume, which I represent with V. And here to differentiate volume from velocity, I use V with little serifs on them. So that's how I will denote volume instead of velocity. And the definition of our density is mass divided by volume. Now here it's asking us for volume, so we need to algebraically rearrange this to give volume is mass divided by density. So we have the mass, 31.103 grams, very precise number. And then we have the material. And why the material is important? Because the material tells us about the density. And it's true that any material has a very specific density. And in fact, any chunk of gold will have a density of 19,300 kilograms per meter cubed. And it's a very large number, and that's because a meter cubed is a large amount of volume. So, of course, it's going to have a large amount of mass. But that is the density of any chunk of pure gold that you have. So we take this and we look at our equation and we say, okay, well then that must mean that volume can be found by taking 31.103, our mass, divided by the density, 19,300 kilograms per meter cubed, and we run into an issue. Now it's very important here to understand that our units need to match up here. And in fact, here the units that are important to match up are that gram and that kilogram. So we need to rearrange this. Now we could do one of two things. We could either put the density in grams per centimeter cubed. Often that is a method that we might use. Or we can take the 31.103 and make it 0.03103 kilograms. Both are absolutely fine to do. For me, I'm actually going to convert the density. And I'm going to convert the density to be not 19,300 kilograms per meter cubed, but instead I'm going to convert it to the other unit that you will often see for density, which is a gram per centimeter cubed. So the first thing we want to do is convert it into centimeters, right? Get from meters to centimeters. And to do that, we know that 1 meter is equal to 100 centimeters. And when we do this, we see, okay, well, meter cancels out with meter, kind of, because there is a pesky 3 right there. So you actually have to do this unit conversion 3 times. So you have to divide by 100, total of 3 times. And that'll take care of our meter. And then we convert from kilograms to grams, and it is 1,000 grams is 1 kilogram. And that cancels out our kilogram. And what we end up with is a density of 19.3 grams per centimeter cubed. Now this is, again, a common way we represent density in grams per centimeter cubed. The reason why is because a meter cubed of volume is a lot of volume. It's not typically seen, so we often use this centimeter cubed for volume. So we divide by 19.3 grams per centimeter cubed. And we end up with 1.612 cubic centimeters. And cubic centimeters is an absolutely fine fine unit of volume, but sometimes we like to use volume of liters. And the conversion between centimeters cube and liters will convert to milliliters, which is a thousandth of a liter. But the conversion from centimeters cubed to milliliters is 1-to-1. So we could rewrite this as 1.612 milliliters instead of centimeters cubed. And that gives us our volume. That's the volume of gold that must weigh 1 troy ounce. Moving on, we take another look at a density problem. And this time it's the density of air. And it's talking about the air that we breathe. So it gives us, again, the material. And now we have the volume. And we ask the question of what is the mass. So again, it's this relationship between density, the material of an object, mass, and volume. The density of air is 1.23 kilograms per meter cubed. Now, when we have kilograms per meter cubed, here we tend to use this value. Why? Because air is very light. It takes a large volume of air to really have any substantial mass. So you might typically see the density of air written in this kilogram per meter cubed. The volume, well, we are given the volume of 2.00 liters. And you might be tempted to say, well, if 1 milliliter is equal to, nope, that's not what I wanted to write. If 1 milliliter is equal to 1 centimeter cubed, perhaps that means 1 liter is equal to 1 meter cubed. You might be tempted to do that, but it's important to know that that is not true. Instead, we're going to find the relationship. How do we do that? Well, 2 liters, we can first convert that to milliliters because I know how milliliters convert. So when we convert it to milliliters, we say 1,000 milliliters. Remember, milli means a thousandth. 1,000 milliliters divided by 1 liter. And that crosses out our liter, so it gets us into units of milliliter. We know 1 centimeter cubed is equal to 1 milliliter, so a 1-to-1 unit conversion here that gets rid of our milliliter units. And then if we want to get into this meter cubed unit, well, we could say that 1 meter is 100 centimeters, and we have to do this 3 times to account for the centimeters cubed. Shouldn't have marked off that centimeter right there. And that would leave us with units of meters. And you do the math here, and what you would find out is that the volume is equal to 2 times 10 to the minus 3, and actually I should pay attention to sig figs here, 2.00 times 10 to the minus 3 meters cubed. So that gives us our volume. So it's not 1-to-1 between liters and meters cubed. It is, however, 1-to-1 between milliliters and centimeters cubed. In any case, we take a step forward and we say, okay, well, what is our mass of air that is in our lungs after we take a deep breath? Well, mass is going to be density times volume. You multiply the volume and the density together, and you would find the mass to be 0.00246 kg. A very, very, very small mass. A small mass that would not necessarily affect our body's total density all that much. However, it does give a little bit of an effect. And what's interesting here is that the effect is large enough that it might tip us from a density that would sink to a density that would float. That's why if you're ever in water and you take a deep breath, you could float, but if you let it all out, you might sink. So it does have a small effect, but it's not going to be drastic. We'll learn more about sinking and floating in a future video. Moving on, right, we talk about density. Why do we do that? We do that because it'll help inform us about how fluids interact. And these interactions that we talk about will be discussed with this idea of pressure. Pressure is the interaction between surfaces. And here we are given the example of a nail being hit with a hammer. That's my drawing of a hammer and a nail. And the hammer hitting the nail is going to push the nail down into the wood, and it breaks the surface because there's a tremendous amount of pressure present. But how much force is present? That might be a question. Well, pressure, we represent with P, not to be confused with momentum, is defined as the force over area of an interaction, right? So an interaction happens over some surface. The pressure from that interaction is going to be the force divided by the area. We have the diameter of the nail, so we can find the area to be pi times the diameter squared over 4. The pressure is given to us at 3.00 times 10 to the 9 newtons per meter squared, a very high value, but high value should be expected here, right? Because a nail can pretty easily pierce through the wood, so we would expect a high amount of pressure. We take this diameter and we need to convert it into meters, but after we convert it into meters and calculate the force by doing pressure times area, we would have 3 times 10 to the 9, and there are some sig figs added on here, right? There's an extra 0.00. It's not going to affect the calculation part, so I'm going to exclude it from the calculation. I'm writing it down just to save a little bit of space. But do know that it is that 0.00 does give us more significance into those digits. So we multiply our pressure term by our area term, which is pi times our diameter, 0.001 meters. So our diameter squared over 4. Well, you take this, you plug it into your calculator, and what you would find is that the force is equal to 2.355 times 10 to the 3 newtons. A large amount of force. And a large amount of force, again, should be expected. When you hit a nail with a hammer, it's going to go from being in a collision with a very heavy object for a very short period of time leads to a large force. So we should expect to see a large force. In any case, that is how you would relate pressure and force and area. Well, we took this idea and we defined a hydrostatic pressure, right? Pressure that is just due to fluids that are above whatever is submerged in water. So the next question deals with that hydrostatic pressure. And if we ask the question, what is the hydrostatic pressure due to the ocean water above the Marianas Trench? Well, that's going to be relatively easy to calculate as the density times acceleration due to gravity times the depth of the water. We'll use h here to represent the depth of the water. Now, an important note here, right? It is asking about the pressure due to the ocean and not the atmosphere above. If we were to be asking about the absolute pressure at the bottom of the Marianas Trench, that's going to be adding on a factor of atmospheric pressure. This would be your absolute pressure, the total pressure from the ocean and the air. But since I'm just asking about the ocean, I don't actually care about that atmospheric pressure addition. In any case, this problem becomes relatively easy and straightforward. It's plug and chug, where we have the density of water, and the density of water is 1.025 grams per centimeter cubed. This is the density of salt water. Pure water has a density of 1 gram per centimeter cubed. Salt water has a little bit higher density. So that's our density. We multiply that by the acceleration due to gravity, 9.8. And we multiply that by the depth, 11 kilometers. But oh wait, we have an issue. Kilometers, we need to convert that. We need to convert it to 11,000 meters. And once you do that, you plug it in, And you find that the depth at the bottom of the Marianas Trench is about 1.10 times 10 to the 6 Pascal. Again, this is not absolute pressure. This is what we would call gauge pressure, but it is just the pressure from the fluid above it, the ocean, excluding the atmosphere. So then we move on to this last problem. Before I get there, I want to give you a warning. This is a calculus-based problem. It's not something of the form I would ask you guys to solve on your own, but I do think it's useful to see the application of calculus and see how it is done, and I'm going to show you in this next problem how you would apply that idea to a problem based on pressure. So the problem states that we have a dam of height 12 meters and some width of 10 meters. Gives us the density of water, and seems to be pure water, not salt water. So 1,000 kilograms per meter cubed is the density. This can be converted to 1 gram per centimeter cubed. We're not going to convert it. I think we want to keep it in kilograms a meter cubed, but that is the density of fresh water. Taking a look at this, it asks us what is the force acting on the dam, and it gives us height, width of the dam, and density of water. So in approaching this problem, you start off with the relationship between force and hydrostatic pressure. And that will be that force is pressure times area. We take a look at this dam and we say, okay, well, I could imagine a very thin strip dy. At that very thin strip dy, the pressure is going to equal rho gh. Technically, this is rho g plus h plus half of dy. I'll show you why that's not going to play a huge role. But we get some pressure rho gh. And then we ask, okay, well, on this thin strip that we're looking at, what is the area? Well, the area is going to be the width of this strip multiplied by the height dy. So the area is width dy. And we say, okay, well, that force is equal to pressure times area. If we take a look at this strip, that would give us the force acting on just that strip. We then move on to take a look at a second strip. Maybe we go a little bit above. My perspective isn't good here, but maybe we pick out a second strip and we find the force on that. And then maybe we pick up on a third strip and a fourth strip and a fifth strip. And we go until we count all of the strips, and then we take the total force by adding them together. But in the limit that dy becomes very, very small, approximately 0, this becomes impossible. You'd be doing an infinite sum. And this is why we use calculus. We use calculus to provide us a methodology that utilizes that infinite sum. So you take a look at this, and we say, okay, in this tiny strip, the amount of pressure on average is going to be rho g times h plus half dy. And the reason why I say half dy is because I'm saying I'm looking at specifically the pressure halfway between. I know in the region that I'm about to color blue, in the region below, I know that the pressure is going to be slightly larger. And in this green region that is above that midpoint, I know the pressure is going to be slightly smaller. So the idea is that we could approximate the pressure as having an average value that is halfway. But in the limit that dy goes to 0, this pressure just becomes rho gh. Essentially, we take that dy to be infinitesimally small. So I'm just going to write the pressure is equal to rho gh, and that's going to be good enough. We then ask the question, okay, well, the area is going to have some small value, and the area is going to be equal to the width times dy. We take these together, and we say that the force is going to be the summation of all of these little chunks of area between 0 and height h, capital H, of pressure, rho GH, times area, width, dy. So we end up with this integral. And again, the integral is just a summation. It's looking at an infinite number of those little strips and adding them together. When we look at this, well, density is not going to change as we go from the bottom to the top. Acceleration due to gravity doesn't change as we go from the bottom to the top. And the width doesn't change. All of these three are constant values. So the force, therefore, becomes rho GW, the density times the acceleration due to gravity times the width of our dam, from 0 to capital H, little h dy. And you ask, well, why don't we take the little h out, the lowercase h? And the reason why we don't take the lowercase h out is because that value of h changes. Depending on if we're looking at the very bottom, if we look all the way down here, h will extend all the way down. So at the bottom, h is equal to capital H. Little h is equal to capital H. When we look at the top, little h is equal to 0. So we do get some change. But interestingly enough, I know that h plus dy plus y, whatever these values are, must equal the total height. But again, we take the limit as dy goes to 0. In those same limit that dy goes to 0, we find that h plus y equals capital H. Okay, well, that's great. What do we do with that? Well, we could rewrite this integral. Density times acceleration due to gravity times the width of our dam. The integral from 0 to capital H, the total height of our dam, is going to be h plus y, capital H. Nope, I messed that up. We replace little h with h minus y dy. And when we do this, we suddenly have an integral that is solvable. And we solve this integral, and we find that the force is equal to the density times acceleration due to gravity times the width of our dam, multiplied by h squared minus 1/2 h squared, where h again is the total height of the dam. H minus 1/2 h, that simplifies to just 1/2 times h squared. So you end up with the force being 1/2 density times acceleration due to gravity times the width times h squared. And this gives you the force felt by the dam. You plug in the numbers, and the force is an extraordinarily high. We have a couple of sig figs here, so I'll include them. 7.06 times 10 to the 6 newtons. So dams do hold back a lot of force, and this is going to be the average force over the entire dam. Again, obviously the force at the bottom is going to be larger than the force at the top, but the idea is that it averages out to be that same value of 7 times 10 to the 6 newtons. Okay, so that covers it for this video. If you have any questions, be sure to reach out. Otherwise, I will see you in the next one.